Welcome, gentle listener, to Sleepy Facts. This is a quiet place, a soft current in the stream of the night where the universe whispers its stories. Here, knowledge arrives as softly as a dream. Settle in and let the world outside gently fade, allowing your breath to find its own slow, peaceful rhythm. Imagine for a moment a star hanging in the velvet dark of space. For millions of years, it breathes, a long, slow inhale of gravity pulling everything inward toward its warm heart, and a long, slow exhale of light, pushing everything away into the coldness of the void. It is a perfect, silent balance, a life held in a single, glowing breath. Tonight, we will watch what happens when that breath comes to an end. We will drift into a dream of the universe where a shadow is born not from an object, but from the weight of a dying star. This star, like all stars, once lived in a state of perfect grace. It was a place where two immense opposing forces found their equilibrium. The first force was gravity, the constant gentle pressure of the star's own immense mass, always pulling inward, always seeking its own center. It is a force of gathering, of holding, of pulling the universe into a single dense point. And deep within the star's core, in its furnace of creation, a second force was born to meet it. Down in these depths, where the pressure is beyond imagining, tiny atoms of hydrogen were crushed against one another with such power that they became something new. They merged, they combined, and in their fusion, they were transformed into a denser element, helium. This new form, this helium, needed less energy to simply exist than the two separate hydrogen atoms that came before it. And so the extra energy, the leftover warmth, was released. This released energy was the second force. It radiated outward from the center of the star, a constant stream of heat and light. The star's long, slow exhale, this outward breath of light, pushed against the inward pull of gravity. And in this delicate cosmic dance, the star found its stability. For millions or even billions of years, it would remain this way, a sphere of peaceful, glowing light, held in perfect tension between the desire to collapse and the need to expand. But this balance, like all things, is finite. The star's heart is a furnace, and every furnace needs fuel. Eventually, the vast stores of hydrogen begin to run low. And if the star is massive enough, truly a giant in the cosmic ocean, it will not simply fade. It will begin to burn its own ashes. The newly formed helium, born from the hydrogen, is now crushed together to form even denser materials like carbon, and then neon, and eventually oxygen and silicon. Each stage is a new breath, a new source of outward pushing light to hold gravity at bay. But then the star begins to create iron. Iron is different. It is an end. When other atoms are fused, they release a whisper of leftover energy. But iron holds on to everything. When it is formed, it saves no energy for the star. It gives nothing back. And so it simply sits in the core of the star, growing heavier, denser, and colder with each passing moment. With no new energy pushing back against the patient, relentless pull of gravity, the scales very quickly begin to tip. The star's long exhale of light falters, while the inhale of gravity grows ever stronger. The collapse is not a slow decline, but a sudden, silent surrender. The energy of this final fall is astounding. The outer layers of the star, a mass millions of times greater than our own world, rush down to meet the core. It is like a hammer of unimaginable size, striking an anvil of infinite density. And the rebound from that blow is what we call a supernova. It is a final, brilliant sigh. Matter and energy are blasted out across the universe in one of the largest explosions possible. From this crackback of light elements, even heavier than iron, are born, forged in the final moment of the star's life, all the way up to uranium, scattered like seeds into the cosmic dust. And what is left of the star after this spectacular farewell? It depends on its weight on the force of that final blow. If the mass of the star, and thus the force of its collapse, was just below a certain threshold, what remains is a neutron star, a small, strange ember in the dark, a ball of matter perhaps no more than 25 kilometers across, yet so densely packed with mass that it equals 1,000,000 Earths. A city-sized sphere containing the ghost of a sun. But if the mass was greater, if the force of the fall was strong enough, physics as we know it breaks down. The very fabric of reality gives way, and we are left with a black hole. When you see an image of a black hole, the perfect black sphere you are looking at is not actually the black hole itself. That is only its shadow, its boundary. Scientists believe the true form of a black hole is a point even smaller and denser than a neutron star. In fact, it is likely infinitely small and infinitely dense. A singularity. A single point emitting a force so powerful that it warps not just space, but time itself. We do not know this for certain, however, and the reason we do not know is because of something called the event horizon. All objects with mass in the universe exert a gravitational pull. It is a fundamental property of existence. But in 1915, when Einstein presented his theory of general relativity, it suggested something more profound. A contemporary of his, a man named Karl Schwarzschild, reasoned from these new equations that there could exist an object so massive and so dense that it could create a gravitational pull so powerful that light itself could not escape. And if even massless photons of light couldn't get out, nothing could. When you look at a picture of a black hole, you are not seeing the singularity. You are seeing the event horizon around it. It is the demarcation line, the silent shore, where gravity has become so powerful that the outward journey is no longer possible. Beyond this line, there is nothing but darkness, a place from which no message, no light, no echo can ever return. It is an edge not in space, but in causality itself. This place, this shadow, has a profound effect on space, but its influence reaches deeper still into the very flow of the universe. For according to Einstein, space and time are not separate things. They are woven together into a single fabric spacetime. And the immense mass of the singularity, concentrated at an infinite point, stretches this fabric so much that the event horizon also marks the point where time stops. Within the event horizon, space and time, as we understand them, cease to be. There is no where or when. This produces a strange and beautiful phenomenon for anyone watching from a safe distance. If you were to observe a piece of matter falling into a black hole from your perspective, as the matter approaches the horizon, it would seem to slow down. Its light would stretch its color, shifting toward red. Its clock would tick slower and slower until just before the event horizon, it would seem to stop altogether. You would never actually see it cross the line. There would be no satisfying final moment, no absorption. Instead, the object would gradually dim, fading over an eternity until you could no longer see it, a frozen memory hanging at the edge of forever. For many years, this was only a dream in the language of mathematics. When first theorized, astronomers and physicists were uncertain if black holes were actually real. They were ghosts in an equation too strange to exist in our cosmos. It was only 40 years later, in 1964, that the first hint of evidence was recorded. Using newly developed X-ray satellites, scientists noticed an object in the constellation Cygnus that seemed to be emitting a tremendous amount of X-rays. But strangely, they could not see the object itself. This was a puzzle. If it were a normal star, it should emit visible light along with its X-ray radiation. But this object was invisible. They called it Cygnus X1. A few years later, as telescopes advanced, they noticed that this invisible source of X-rays had a partner, a star, caught in a binary orbit with it. This cosmic dance allowed scientists to calculate the mass of the unseen object. They discovered it was 15 times more massive than our sun. The densest known objects at the time, neutron stars, had an upper limit of only 3 times the mass of the sun. This invisible companion was far too heavy. And so, scientists realized that this was most likely the first ever discovered black hole. Since then, we have found many more. Massive ones seem to exist at the silent centers of most galaxies, including our own. And with new technology, we have even managed to take photos of some dark blots against a swirling ring of light. That light, that ring of matter, is called an accretion disk. And it is how we are able to see the unseen. While a black hole itself can emit no light, the matter that falls toward it can. The X-rays from Cygnus X1 and from other black holes do not come from within the event horizon. They originate from the accretion disk, where infalling matter gas dust. The remains of unlucky stars gets heated to millions of degrees Celsius through intense friction as it spirals inward. A black hole with no matter falling into it is almost perfectly invisible, a quiet tear in the fabric of the night with no bright accretion disk to mark its place. Exploring these strange regions is still a new and developing field of physics. There is still so much to learn, so much that is hidden behind that silent horizon. And as we learn more, we may wonder, could a black hole ever stop being a black hole? Or will it grow forever until there is no matter or radiation left in the universe for it to consume? It would seem so. But in 1912, the physicist Stephen Hawking imagined something else. In a paper he titled Black Hole Explosions, he suggested that there was in fact a way that energy and thus mass could leave a black hole. The thought widens, becoming air. Part 2. To understand this faint whisper of escape, we must first get into some extremely strange and beautiful theory. We need to look closely at the very fabric of reality. And to begin, we must ask a difficult question. What is nothing? Imagine for a second a patch of space with nothing inside of it. It has no atoms of space dust, not even a single photon of radiation passing through it. As near as can be seen, nothing exists within it. And yet, is there really, truly nothing there? Something fundamental exists even in the most perfect vacuum. We can tell that this is the case when a beam of light travels through it. If you are familiar with the properties of light, you will know that it is a wave. Waves of electrical and magnetic charge, constantly moving forward in a straight line. But let us linger on that word, a wave. A wave in the sea is energy moving through the water. If you were to look at a single particle of water, it is not really going anywhere except in a small circle. And yet, because it passes its energy to the atoms next to it. That energy travels towards the shore in a constant flowing motion. Similarly, a sound wave moves by passing energy between particles of air, with each particle only moving a tiny bit before passing its energy to the next one in line. But in our vacuum of space, where there is nothing, where our photon of light is traveling in waves, have you ever stopped to wonder what exactly is waving? This hints at a fundamental something that exists even in nothing, a fabric that makes up all of reality itself. Quantum physicists call this something a quantum field. Quantum fields are difficult to wrap your head around, but they are a beautiful way to imagine the universe. Think of them as the silent, invisible strings of a vast instrument, stretching across all of space and all of time. In fact, scientists believe there are several of these quantum fields, all overlapping, all intertwined, covering every single patch of the universe, past, present, and future. Each field defines a particular type of something. One field might define all of the electrons in existence, while another may define the quarks that make up an atom. Where nothing can be found, the quantum field is quiet. It is like a guitar string that has not been strummed a still surface of a lake. But wherever in time and space mass or energy can be found, the quantum field is resonating at that point. It is vibrating like a note being played. And when that resonance, that vibration reaches a certain level, the universe expresses that note as a particle, say an electron or a photon of light. In this dream of the universe, the particle is not just reacting to the field. The resonance is the particle. An electron is nothing more than a resonating section of the quantum field that defines electrons. And this is true for all energy and all matter. The entire universe you see around you is just the sound of these fields resonating together. A song being played on invisible strings. So how does this cosmic song tie into the idea of an exploding black hole? Going back to Hawking's paper, he hypothesized that black holes would release energy slowly over time in tiny, almost imperceptible quantities. And because energy and mass are two expressions of the same thing, according to Einstein's famous equation, this slow release of energy would inevitably result in a reduction in the black hole's mass. It would begin to evaporate. As the black hole shrinks, the rate of this energy release would speed up, getting faster and faster until in the very last moments of its life, it would release a final gargantuan burst of energy before vanishing entirely. But how can this be true? The event horizon is a point of no return. So how could radiation ever leave it? The answer is a strange one, and it relies on ideas from the quantum world that go against our day-to-day experience. To begin to understand Hawking's theory, we need to return to the idea of the quantum fields, those silent strings of the universe. Due to a principle of quantum physics called Heisenberg's uncertainty principle, it turns out that these strings sometimes start strumming themselves. Essentially, when we look at the universe on the very tiniest of scales, it becomes impossible to know everything about it at once. You cannot know both the precise location and the precise direction of travel of an electron, for instance. Not because our tools aren't good enough, but because of a fundamental law about the nature of reality itself. And when you apply this principle of uncertainty to the quantum fields, it gets even stranger. The fields are always fluctuating, always shimmering with a quiet energy. And because of this uncertainty, pairs of particles, a particle and its antiparticle, can actually pop in and out of existence from these fluctuations. The universe allows this to happen as long as they only exist for a very, very short period of time. You might think this can't possibly be a real thing. Matter does not just pop into existence. We would have surely noticed this by now. However, in an experiment done by a physicist named Hendrik Casimir, evidence was found that suggests this might actually happen. He took two plates of conductive metal and placed them extremely close together. So close that only certain sizes of these fleeting virtual particles could pop into existence between them. This limited the number of such particles that could appear in that tiny gap. But on the outside of the plates, all types and sizes of particles could still pop into existence. This meant there was a difference in pressure exerted on the two sides of each plate. Theoretically, the greater pressure from the particles on the outside should push the two plates together. And in the test, this proved to be the case. An unseen force born from nothing. You might think that particles appearing out of nowhere would defy the laws of conservation. And you would be right. So to balance the scales, whenever a virtual particle appears, a second particle also pops into existence to pair up with it. But while one of the particles is matter, the other is antimatter. A 1 and a -1. Thus, the overall balance remains at 0. The universe is happy. And on top of that, these fluctuations in the quantum field quickly crash into each other and annihilate, removing them both from existence again. This is why, for the most part, empty space remains empty. So the quantum fields are constantly resonating, constantly creating these fleeting pairs and constantly cancelling each other out. But what would happen if you stopped only some of those fields from resonating. This is where black holes come in. They act a bit like putting your thumb on the guitar string of the universe. Due to their event horizons, certain resonances in the quantum fields are dampened down while others are not. Hawking imagined a quantum field that resonated through time, stretching from before the existence of a black hole into the future after it had formed. Before the birth of the black hole, all is normal. The quantum fields are all resonating freely, and the virtual particles can cancel each other out. However, the emergence of the event horizon changes the curvature of space. And as Hawking looked at the math, he realized that in this new curved space, not everything was being cancelled out anymore. Some of the virtual particles were now missing their opposite numbers. He realized that after the black hole had formed, there were resonances left over, traveling away from the black hole into space. And these resonances perfectly match the shape of thermal radiation. Radiation is energy, and energy cannot form from nothing. As the curved space around the black hole was creating this radiation, the black hole itself would have to pay the price. Every piece of this Hawking radiation would thus coincide with an equal amount of energy lost from the black hole, which over an immense stretch of time would reduce it down to nothing. It is like money spontaneously appearing outside of a bank, while inside the bank, the money in the vault vanishes. Proving this is extremely difficult. Hawking predicted this radiation would be colder than the cosmic background radiation that already fills the universe. Its wavelength would be as long as the black hole's event horizon itself. And as some black holes have event horizons the size of entire solar systems, we have no way of detecting such a faint, stretched out whisper. However, scientists have recently taken steps to proving it in a laboratory. At an institute in Israel, researchers came up with an idea to get around the difficulty of measuring a real black hole. They created an analog, a sonic black hole. They relied on the fact that sound moves much slower than light. So it is much easier to create a medium that moves faster than sound. When it does, any sound waves traveling in the same direction can never quite escape it, much like light at an event horizon. Interestingly, Hawking's math worked for these sonic black holes just as well as it did for gravity-based ones. And so, Hawking radiation ought to be detected from it. After repeating the experiment 97,000 times, the researchers detected it. A faint hum of sonic radiation matching Hawking's predictions. This does not prove that Hawking radiation is definitely real for actual black holes. But the fact that the math worked for this sonic analog is a strong implication that he might be onto something. So, if you fell into a black hole, could you ever escape? Probably not. However, if you waited until almost the end of the universe, the black hole may just radiate away, bit by bit, until the mass and energy that made up your existence was completely returned to the cosmos. A slow unmaking, a return to the light. And that is not the only strange thing about black holes. Their very existence and this faint whisper of their unmaking implies something quite worrying and quite beautiful about our own reality. When you are walking on a beach and you leave a footprint in the sand, there is no question in your mind that it is your foot that caused the footprint. The order of things, the flow of cause and effect is simple and clear. It seems laughable to even need to assert it. You made the footprint. The footprint did not make you. But what if it did? What if, on the vast cosmological scale, the fundamental relationship between the foot and the footprint is a little more blurred than you would intuitively think? Shockingly, due to the nature of black holes and the faint warmth of Hawking radiation, there is some evidence that this might just be the case. To begin with, we must return to this faint warm light. The most important thing to bear in mind about it is that it is non-local. This means that it does not appear from the black hole itself, but from the area of space around it. When we say this, we do not mean from just beyond the singularity, but still within the black sphere of the event horizon. Space as we know it doesn't exist there. That black ball you see is simply the line between an escapable curve and an inescapable one. We do not even mean that it happens right up against the event horizon, though that is sometimes how this theory is portrayed. The image of two particles popping into existence with one falling in and one escaping. The truth is stranger. The region of space where this radiation can be born is several times the size of the event horizon itself, a distance that can stretch for billions of kilometers. And when the largest black holes can comfortably fit multiple solar systems inside of their event horizon, the idea that a photon of radiation can pop into existence the same distance again outside the horizon is difficult to comprehend. It happens even in a place where there is, for all intents and purposes, nothing there. So in short, it is not so much that Hawking radiation is coming from the black hole directly. Instead, it is coming into existence from the curvature of space that the black hole is creating. And it can happen very, very far away. But if that is true, then things work completely opposite to what we might expect. Consider the order of events. First, energy in the form of radiation leaves the curvature of space. Then, because energy must be conserved, the curvature of space itself lessens. And only then, as a result of this reduction in curvature, does the black hole shrink. This is a strange and profound reversal. This is like the footprint in the sand getting smaller. And because of that, the foot that made it shrinks accordingly. It feels deeply wrong. Things cannot possibly work that way. And yet, Einstein himself hinted that such a thing might be possible. In one of his equations, he stated that the curvature of space-time was proportional to the mass energy of an object. But proportional is not the same as causational. There is no rule in that relationship that says one must cause the other. We are comfortable with the idea of changing the mass and so changing the curve. But the mathematics works just as well if you go the other way. If you change the curvature to change the mass. If this is true, then it hints at a universe where mass is simply a projection caused by the shape of space. When you shine a light at your hand, it makes a shadow on the wall. The shadow is a projection caused by the existence of your hand interacting with the light. Normally, in this analogy, you might be forgiven for believing that we are the hand, that it is our mass that creates the curvature of space around us. And yet, do we really know that it doesn't work the other way around? Are we simply projections, shadows on the wall of the universe being brought into life by something more fundamental, something happening in the curvature of space-time? And yet, we are going around thinking that we are the thing that is real. Given that all you know is the reality you experience, it would be difficult for you to be able to tell the difference between the two scenarios. But if the study of the universe has taught us anything, it is that if there is no way of telling the difference between two situations, then we cannot completely dismiss that we are in one and not the other. This is an idea called relativity. And it began not with Einstein, but with Galileo in 1632. He imagined two rooms. One is on a ship sailing on a perfectly calm sea. The other is on land. Both rooms are soundproof and have no windows. The only difference between them is that one is moving and the other is not. Can you tell the difference from the inside? You might think that you would be able to sense the movement. But this is not the case. For instance, right now, as you are listening, you are careening through space at over 100,000 kilometers per hour due to the Earth's movement around the sun. And yet, if you are sitting or lying down, it is likely you would have said you were not moving at all. Galileo realized that there was no test that could be done to tell the difference between the two scenarios. He even found that if you dropped a ball on the ship from your perspective, it would look like it fell straight down, even if from the perspective of a person on land, it would look like it was falling diagonally. He realized that if you remove all frames of reference, say by being in deep space, there is no way of telling if a planet is moving towards you, or if you are moving towards a planet. According to relativity, both are equally valid interpretations. Einstein took this idea further. He imagined two rooms again, but this time he was making an observation about gravity. If you were inside a windowless room floating in the vacuum of space and someone started accelerating your room upwards, say by strapping a rocket to the bottom of it, if that rocket accelerated at just the right speed, it would feel identical to standing in a room on the surface of the Earth. In other words, there is no way to tell the difference between the acceleration caused by gravity and the acceleration caused by a rocket. Both of these ideas rely on the principle of inertia, that objects do not like to move if left on their own, and do not like to stop moving once they have started. But why would it feel to the person in the room with the rocket as if they were under the effects of gravity? Or perhaps a better question, why would it feel to us on Earth as if we were being accelerated upwards by a rocket? The Earth is not expanding, pushing us with it. Einstein realized that the two felt similar because they were in a way the same thing, a form of acceleration. But there is another form of acceleration that better explains how gravity works than simply pushing on an object like a rocket does. Consider a spinning fairground ride. If you have ever been on such a ride, you will know the power of changing direction. As the ride gets up to speed, you feel a constant force pressing you against the wall. Even when the ride is spinning at a constant speed. This is because your body is trying to move in a straight line. But the curvature of the ride is forcing you to alter your direction. The battle between your own inertia and the wall trying to alter your path manifests as the force you feel. And as far as acceleration is concerned, there is not much difference between the earth beneath you accelerating you up and you trying to accelerate down. Einstein realized that this form of acceleration caused by a curving path was the best explanation for gravity. He came up with a theory that matter and energy cause a warping in the space around them, much like how a heavy ball might bend the surface of a taut rubber sheet it was placed on. The larger the mass, the greater the curvature. And once space was curved, any object trying to travel through it would be deflected by that curve. In the words of the physicist John Wheeler, space tells matter how to move. Matter tells space how to curve. For small masses, this curve in space is very slight. But for incredibly dense masses, this curvature could get so great that it would be impossible for an object that got too close to ever escape. These are the conditions we find near a black hole. So going back to our very first thought of the footprint and the foot. If a black hole is the foot, the curvature of space around it is the footprint. And normally, our intuition is clear. The black hole tells space how to curve, and once curved, any object moving near it is told how to move. But when we remember the faint whisper of Hawking radiation, born not from the black hole, but from the curve in space itself, a strange thing happens. The order of things begins to feel less certain, less solid. The gentle curve of space holds its own deep secrets. Of course, this is all just a theory, a dream born from mathematics. There is no hard proof that Hawking radiation is even a real thing, though the whispers from the lab suggest it might be. But it is a beautiful and strange thought to hold as you drift. Even if it does prove to be the case that reality is a projection, it is not going to affect your day very much. You will still think and feel, and that is more than enough reason for you to be. But it is an example of how, when we start to examine the very fundamental building blocks of reality, by exploring the weird warping effects of black holes, it can cause us to challenge our assumptions about our very nature. These shadows affect our reality, and they affect our universe. They are the end, the final quiet destruction of matter and time. And yet, what if I said to you that they might also prove to be our salvation? What if these places of ultimate ending could also be a source of beginning? Black holes might hold the answer to traveling faster than the speed of light, and to solving the need for energy in ways we have only just begun to imagine. And they do so, as we have come to expect, by messing with the very fabric of reality itself, and by completely countering our expectations of how the universe should work. To understand how a black hole ignores the usual limitations on speed, and does so in a way that could be used without ever having to cross its silent shore, and how it produces near limitless energy at the same time, we are going to have to understand more about the features of black holes than we have covered so far. It is, of course, very difficult to say much about a black hole's features at all, precisely because of the event horizon. We cannot see what is inside. In fact, there are only 3 things we can say about a black hole with any degree of certainty. They have mass, they have charge, and they have angular momentum. They have a weight, an electric breath, and a silent spin. You might wonder how we know these things, given that no light can leave them to tell us their secrets. The key is that all 3 of these characteristics can be felt outside the event horizon. Their influence extends beyond the point of no return. Charge, for instance, works the same way around a black hole as it does around any other charged object. If a black hole is charged, it will attract objects that have the opposite charge and repel objects that share its charge. Think of it like a giant invisible magnet pushing and pulling on the universe around it. Scientists can track the dance of charged particles as they approach a black hole. And by seeing how they move, they can predict the charge of the black hole itself. Interplaying with this is mass. The mass of a black hole can also be felt outside its dark sphere. In fact, it is the main creator of the event horizon in the first place. This is because mass creates gravity. And so it is possible too to calculate the mass of an unseen object by watching how other things move around it, how far away they are before they start to accelerate towards it, and how quickly they fall. And finally, angular momentum, or spin. It is possible to detect the spin of a massive object. And as we will see, this silent turning has the most profound effects of all. For now, let us just accept it as a given and recognize that black holes are defined by these three simple things. And yet, from these simple properties, an incredible diversity of scale is born. The smallest known black holes have a mass that is comparable to that of our own moon. And they fit all of this into a space that is just 0.2 millimeters in diameter. It is an incredible thought, something thinner than a human hair packing the entire weight of the moon. And that is just the smallest ones. Stellar black holes have a mass equal to 10 times our sun and have a diameter of about 60 kilometers. Intermediate black holes are the mass of 1,000 suns and fit all of that into a sphere smaller than the Earth. And then there are the largest black holes, the ones that dwarf us. Their masses are between 100,000 to 10 billion times the mass of the Sun. Their sizes range from a fraction of the distance between the Earth and the Sun to a space large enough to swallow our entire solar system 400 times over. And yet, other than these three features, mass, charge, and spin, there are, in theory, no other differences between them. If you put two black holes in the same room and made sure they had the same mass, charge, and spin, it would be impossible to tell them apart. They are the simplest, most perfect objects in the universe. These three features are enough, however, to have some truly interesting effects on the area of space outside a black hole. Traveling inside one is impossible, but we think we know a few things that must exist within. Beating in the heart of a black hole, there is thought to lie the singularity. In truth, this is the black hole. The sphere we see is only its shadow. We are not certain what the singularity actually looks like because no light can ever escape it to tell us. But in our models for the simplest black holes, the ones that do not spin it, is a single point, a place where all the mass of the black hole is packed into a space that is infinitely small, so that it is infinitely dense. For a rotating black hole, this is more like a little spinning ring. Otherwise, it would be difficult to define spin for a point that has no volume. Our current physics gets very strange around such a black hole. Our ideas about singularities are not yet complete, a sign that we have more to learn. It may one day turn out that they do not exist in the hearts of black holes at all. But for now, this is the extent of our knowledge. And whatever it is that lies inside a black hole, it powers a strange and wonderful engine. Because like most objects in the universe, it spins. Oh, and does it spin? As we travel out from this imagined center, we pass through the event horizon. To a person watching from the outside, they might see you slow down to a complete stop as you approach it. But from your perspective, it might seem like time is flowing normally. Normally, that is until the entire universe outside the black hole runs its course in an instant. Because time out there is traveling so much faster than it is for you. The only evidence you might have that you have crossed the event horizon at all is because of something that exists just outside it. The photon sphere. In a zone just outside the event horizon, there exists a point in space where if a photon enters it at just the right angle, it will be caught in a perfect orbit around the black hole in much the same way the moon perfectly orbits the Earth. This infinitesimally thin zone is known as the photon sphere. And given the number of photons that have flown past black holes in all the millions of years they have existed, it is probably filled with light. A shimmering shell of captured photons endlessly circling the darkness. And it is just outside here that we find the zone that interests us, the ergosphere. This is the zone around a black hole where we can most easily detect its spin. And this is because in this zone, it is impossible for us not to move. You see, mass affects space. But it might be more accurate to say that mass drags on the space around it. As it moves, it brings a little bit of that space along with it for the ride. And when an object as massive as a black hole spins, there is an effect known as frame dragging. To put it simply, reality itself around the black hole begins to spin in a whirlpool that cannot be fought against. Anything caught within the ergosphere is spun around the black hole because the very frame of reference it sits in is being pulled along. It is like a person standing still on a moving walkway. The greater the spin of the massive object, the faster this happens. And in the ergosphere, this can occur at a speed so fast that by the time you get to the event horizon, space itself is moving faster than the speed of light. You would need to travel faster than the speed of light in the opposite direction just to stay at a relative standstill, which of course you cannot do. But isn't this against the laws of physics? doesn't Einstein say that nothing can travel faster than the speed of light? The answer to that is yes. But black holes have found an interesting loophole. This rule only applies locally, right where you are in your own small patch of space. Nothing can go faster than light. But it is possible for the frames of reference themselves to move away from each other so fast that objects in them appear to be breaking this light barrier. Frame dragging is a real thing. It is by measuring it that scientists can learn the spin of a black hole. And according to a man named Roger Penrose, there may even be a way of exploiting it. If you were to send a rocket into this section of the ergosphere, the rocket would speed up, caught in the whirlpool of reality. Once it had gained enough speed, it could then fire a propellant, pushing itself out of the whirlpool again. But now, traveling at a much faster speed. This method, named the Penrose process, could hypothetically allow you to gain energy equal to about 20% of the mass of your rocket. And while that might not sound like much, remember that according to Einstein, that 20% of mass would produce an amount of energy equal to itself, multiplied by the speed of light squared. An almost unimaginable amount of energy. To harness this colossal kinetic energy, all you would need to do is travel to the nearest black hole and enter its spinning ergosphere with a rocket capable of surviving. An easy task, perhaps a little impractical for us for now. But the implications for faster-than-light travel that black holes demonstrate through frame dragging might just offer us the key to one day beating the light barrier for real. Not by going faster than light ourselves, but by somehow convincing the frame of reference we are in to travel at those faster speeds, just like they do around a black hole. The spin continues, a silent promise in the void. This silent promise, this spinning of space itself, hints at possibilities beyond our imagining. And yet, for all their power, for all their immense and inescapable pull, here is another surprising thing about black holes you may not have known before. Falling into one is a lot harder than it sounds. You might expect it to be relatively easy. After all, they are the ultimate absorbers, the largest sources of gravity out there. Shouldn't it be easier to fall into them than any other thing in the universe? It is a natural thought, but paradoxically, your intuition is wrong. These galactic mouths are one of the hardest places in the universe to actually get inside. So much so that during his lifetime, Einstein himself believed you couldn't get inside them at all. It would seem to be like a slide that gets steeper and steeper the further along it you go. You would expect to speed up more and more the closer you get to the black hole's center. And while this is right, it is also wrong. You do speed up. So much so that your speed will begin to approach the speed of light. However, in almost all circumstances, you will not find yourself approaching the center of the black hole. And this is not some strange quirk of time or relativity. It is something that would be observable from whatever frame of reference you were watching from. To understand why we must look again at the real-world example of an accretion disk. Black holes are at their very heart very simple. In what is known as the no-hair theorem, they are said to be devoid of almost any feature. They have charge, mass, and spin, and that is about it. And so, an accretion disk is not actually a necessary part of a black hole. They can exist just fine without them sitting there, dark and unobservable in space. However, when mass, such as an unlucky star, strays too close to the black hole's gravitational pull, it can be torn apart by the vast forces at work and sucked towards the black hole's center. Strangely enough, though, this matter does not all immediately fall past the event horizon. Instead, the matter usually gathers into a sort of flat spinning ring that orbits around the black hole just outside that silent shore. And while eventually it does all enter this process, can take a very, very long time. Some accretion disks take hundreds of millions of years to be completely absorbed. So what is going on here? Why does the matter not simply enter the black hole? The answer is that it comes up against a surprising and beautiful principle of physics known as the conservation of momentum. The idea is simple. If you have a group of objects, the total amount of motion of those objects must always remain the same. No momentum can be lost. If you have a rocket on a launch pad with zero momentum, it can only give itself momentum by firing a propellant in the opposite direction. Once you add up the amount of momentum given to the rocket going up and the amount of momentum given to the propellant going down, the total remains at zero. This law is always kept, even when it seems like it is not. You would struggle to move anywhere without a floor to push against. The momentum you give to the floor must equal the amount of momentum given to you, but in the opposite direction. You just don't notice it because the floor is so much bigger than you are. But what has this got to do with falling into a black hole? Well, consider this next example, this time to do with angular momentum, the momentum of spinning. Imagine a ballerina turning on a single point in a pool of soft light. Her arms are outstretched and her spin is slow and graceful. The particles in her hands have momentum. They are moving a certain distance in a certain amount of time. Now watch as she tucks her arms close to her body. Suddenly, she is spinning much faster. This is a classic, beautiful example of momentum trying to be conserved. The momentum in her hands is still trying to travel at the same speed it was previously traveling at. But now, Because her arms are close to her body, her hands are traveling a much smaller distance to complete one revolution. And as a result, that revolution is completed much faster. This causes the ballerina to spin faster when she tucks her hands in and slower when she stretches her hands out. Now imagine this on a cosmic scale. In most scenarios, matter does not fall in a perfectly straight line towards a black hole. Almost always, it will miss it slightly and will start spiraling in towards its center, caught in the black hole's gravity. It now has angular momentum. And just like the ballerina, as it gets closer towards the center of the black hole, it starts speeding up, moving on a smaller and smaller orbit. It gains more and more angular spin the further down the gravity well it falls. If you want to go a little further in, you have to spin a little faster. However, unlike the ballerina, this matter has the speed of light to contend with. Nothing in the universe can travel faster than the speed of light. This is a fundamental law. So what happens to our spinning matter as it falls further and further into the black hole? Due to the massive forces and the deep curvature of space, it eventually reaches a point where it cannot go any faster. It has hit a roadblock, and because it cannot spin any faster, it cannot fall any further into the black hole. This has several profound effects. To begin with, as you can imagine, it creates friction. All of this matter spinning at such blistering speeds around the edge of the event horizon starts bumping into each other. And when this is taking place at near light speeds, things get very, very hot. Matter in a black hole's accretion disk can reach temperatures up to 10 million Kelvin. This is enough to melt anything down to a hot plasma. All these constant collisions pummel the atoms involved, causing them to give off more and more of this energy, like squeezing water from a stone. This reduces their mass. Between 10 and 40% of an atom's mass is given off this way in the form of pure energy, which then radiates out across the universe. For a moment of quiet comparison, consider the nuclear fusion that takes place in the heart of our sun. That process converts only about 0.7% of mass into energy. Let that sink in for a moment. Consider how bright the sun is with its tiny fraction of a percent. And then imagine the light that can be born from the edge of a black hole. The brightest of these disks are known as quasars, and they can reach brightnesses that exceed 1,000 times the total brightness of every star in the Milky Way combined. A single point of light outshining a galaxy. And in this brilliant light, there is a kind of release. The good news for the matter trapped in this spinning dance is that as it radiates this energy, it also sheds some of its momentum. With the departing light, A little of that forward motion is carried away, allowing the matter to slow just a little. More momentum is shed by imparting it to the matter further out from the center of the disk. As the fast-moving particles near the horizon knock into the slower particles moving just above them, they give them an extra push, and in doing so, they slow themselves down. In this way, through light and friction, matter slowly, patiently begins to lose its angular momentum and begins to finally fall into the black hole itself. But there is another way that momentum can be shed, a way that creates one of the most breathtaking and striking features in the known universe: their jets. We do not understand everything about these jets. We do not know for certain how they form or what exactly they are comprised of. And only a small fraction of black holes with accretion disks seem to have them. But our current theories suggest they are caused by the immense magnetic forces that are created by the spinning disk, or perhaps even by the rotational power of the black hole itself. It is likely that as the accretion disk spins with all of its moving electrically charged particles, vast and powerful magnetic fields begin to form. The power and the shape of these fields are such that there is only a narrow channel at the north and south poles of the black hole for particles to escape. These magnetic fields may work to channel particles down a narrow, invisible barrel. Particles moving at near relativistic speeds have only one direction they can go. Perhaps they are like the slow, steady release of steam from a kettle fired out through the only gap that exists in the face of this incredible gravitational and thermal pressure. And when they go, they go. Relativistic jets travel further than the galaxies they originate from, and are often millions, if not billions, of light years long. One such jet has its X-rays reaching Earth from a distance of 12.7 billion light years away. A faint whisper from a time when the universe was very young. This is because the radiation produced by such jets is very focused in one direction. It is an effect known as relativistic beaming, or the lighthouse effect. When the beam is pointed away from us, it is much harder to see. But when it turns to face us, we see its incredible brilliance. Take, for example, the now famous image of the galaxy M87. In it, a relativistic jet is clearly detected, a stream of light coming towards us. There is very likely another jet, but we cannot see it because it is going in the other direction, away from our line of sight. It is worth remembering as you picture this, that this energy does not come from the black hole directly. Nothing can escape from within the event horizon. Instead, this matter and radiation are born from the swirling, fiery accretion disk. that surrounds the black hole. And again, much about these jets is still theoretical. We can see them, we can even observe them moving over time, but we do not fully understand them or what gives them their incredible power. Our understanding of accretion disks does not even fully explain how all of the momentum is conserved. There is still some mystery about where it all goes, but the sheer power at play is undeniable. Einstein may have been wrong in his belief that it was impossible to fall into a black hole, but when some of these objects are firing material away from them at near relativistic speeds for distances that span entire galaxies, well, it is evidently possible to not fall into them too. And once you factor in the force of matter that is millions of degrees hot, pushing out at you as it attempts to shed its own spin, you begin to see a different picture. The place that pulls everything in is also a place that pushes things away with an unimaginable force. A silent, cosmic breath, both in and out. So we have seen how the awe-inspiring effects of a black hole can span entire galaxies. The quiet pull and the brilliant, fiery exhale. It begs the question, how big can a black hole actually get? If this is its breath, how large can the source of that breath become? Finding the largest black holes, it turns out, is not difficult. All you need to do is look to the silent centers of large galaxies. Here, like sleeping giants, lie the supermassive black holes. They have grown since their formation billions of years ago. As more and more matter falls into them, continually increasing their mass. The very largest of these can be billions of times the mass of our sun. And yet, here, a gentle puzzle emerges in the cosmic story. It may come as a surprise to you to realize that some of the most massive black holes we know of are actually the youngest. When we look at distant galaxies, we are also looking back in time. Light does not travel instantaneously. It takes time to cross the vast emptiness of space. And so a galaxy that is billions of light years away is showing us a picture of itself from billions of years ago. We are observing it as it was when the universe was only a few billion years old. Pretty young for a galaxy. Surely, though it should be the case that the nearer and thus older supermassive black holes are more massive. They have had so much extra time to consume the matter falling into them. So what is going on here? The very largest supermassive black hole we know of is known as T-on 609. Its mass is an almost incomprehensible 66 billion times the mass of our Sun. By itself, its mass is comparable to our entire Milky Way galaxy. However, TON 618 is exceptionally far away. The light we are seeing from it has been traveling for 10.8 billion years to reach us. This means we are observing it as it was 10.8 billion years ago. It can be at most around 2.8 billion years old in this snapshot of time. By comparison, our own Milky Way galaxy is approximately 13.6 billion years old. Yet, the supermassive black hole found at its core, Sagittarius A star, is only 4 million solar masses, a whisper of a giant in comparison. The Andromeda Galaxy's supermassive black hole, while bigger, is still only 200 million solar masses. One of the big factors to consider here is the difficulty in detecting and measuring these distant shadows. This is still a very new field of research. Technology has only just allowed us to start observing black holes in the last few decades. And even then, we can often only observe the bright chaotic area surrounding them. In fact, most of the distant black holes we know about can only be seen because they are quasars. Tone 618 is a quasar. This means that matter is pouring into its accretion disk at an incredible rate. And because of this, it has erupted into a blaze of light. A quasar can only be sustained as long as matter is falling into it. The friction in the disk is so great that by itself, it can produce thousands of times more light than entire galaxies combined. Ton 618 produces as much light as 140 trillion suns, completely outshining the galaxy it resides in, to the point that we cannot even see its home. And because quasars are the brightest objects in the universe, they can be seen from very, very far away. So one reason for the largest black holes appearing to be far away is down to something known as the Malmquist bias. This is where brighter objects that are further away appear more plentiful, when in reality, we simply cannot see the dimmer objects at that same distance. It implies that there may be an argument that the largest supermassive black holes are actually distributed fairly evenly throughout the universe. If a galaxy has a very large black hole, but it is not currently a quasar, it means we will not see it after a certain distance because a galaxy is much, much dimmer than a quasar. It suggests that the largest black holes may be scattered evenly through the night, but we can only see the ones that have left their lights on. Another reason why we see the biggest black holes far away, and thus in the distant past, is due to the nature of the universe itself. Shortly after the Big Bang, the universe was a much smaller, denser place. Matter was a lot closer together, and so quasars were more common back then because they need extreme amounts of matter falling into them to give off their brilliant light. there was simply a lot more gas around during the early stages of the universe. Over time, two things have happened. The universe has expanded, and the gas within it has been converted into stars. Some of the largest of these stars eventually turn into neutron stars and black holes themselves, meaning their matter is never recycled back into gas clouds. Less available gas means less gas will fall into a supermassive black hole. The feasting has slowed. There is a theory for the fate of the universe that is based on this slow decline called the Big Freeze. It suggests that after some trillions of years, all the gas in the universe will eventually be converted into black holes and the light will go out. Even now, we see some galaxies where their gas has been completely used up, meaning no new stars can form. These are called elliptical galaxies. Spiral galaxies, like our own, still have swirling arms of gas and dust, and thus can still produce new stars. It is interesting then that most of the largest supermassive black holes appear to be in these quiet elliptical galaxies where there is no gas left. Gas needs to lose its momentum to fall into a galaxy's central black hole. And in elliptical galaxies, it seems this has already happened. Their central black holes are likely to be much bigger because of all the infalling matter they consumed in their youth. In spiral galaxies, this great infall hasn't happened to the same extent. And so black hole growth probably occurred rapidly in the early chaotic and crowded universe, but has slowed down now in our more spread out and settled time. This might be why there is no quasar within 500 million light years of us. As the universe ages and things become less chaotic, the number of active quasars has decreased, which means the only quasars we can see, some of which are the largest black holes we know of, are the ones that happened a long time ago. So why are the largest supermassive black holes often the youngest? Although it may appear that way, it might not actually be the case at all. We can measure the distant bright quasars simply because we can see them. The older, closer black holes may also be large, but because they are no longer shining so brightly, we haven't found them yet. As our studies continue and our technology improves, we will start to get a more complete and perhaps more peaceful picture of the universe around us. We have spent a long time with these fascinating regions of space-time where the universe is pushed to its extreme. But despite all the attention they have been given, black holes are not the only way space-time can show off its beautiful silent curves. In theory, there can be equally curved regions of space-time called white holes, and they get their name because they are in many ways the exact opposite of black holes. And in some cases, a black hole and a white hole can be connected by a totally different kind of space-time called a wormhole, a kind of quiet, limbo zone between parallel universes. If you have heard of space travel through wormholes and thought it was not more than a fancy of science fiction, it is an easy thought to have. After all, even though these regions are possible in theory, there is not any evidence that white holes or wormholes actually exist in our universe. But 100 years ago, it was the black hole that was purely theoretical. And now, we think there are literally billions of them out there for our telescopes to see. So let us drift for a moment into these other stranger possibilities. What are these other holes that we can have in space-time? And what do they look like if they are real? To begin, let us start with a simple analogy. If I ask you to imagine a cone, you will probably think of either something that points up like a traffic cone or something that points down like an ice cream cone. These are what we think of as cones in the real world. But if you write down the most general mathematical equation for a cone and try to graph it, you will get something that looks like two cones glued together at their tips. A mathematical cone has two halves, one that points up and one that points down. What we think of as cones are actually just chopped up pieces of the full mathematical cone. Black holes are exactly the same way. Many of the black holes we see in the universe are the remnants of massive stars whose extreme gravity caused them to collapse in on themselves. Once a black hole is created, it becomes permanently separated from the world around it by that silent spherical barrier, the event horizon. Anything can fall in, but nothing, not even light, can come out. This structure of space-time can be neatly summarized in what physicists call a Penrose diagram. It is a way of representing an infinite space-time in a finite drawing. In this diagram, light travels upwards at a 45-degree angle. This makes it easy to see the regions where light can or cannot enter. The diagram shows our regular universe containing the original star before it turned into a black hole. And it shows the black hole itself separated from the rest of the universe by its event horizon. You can see how it is easy for light to enter the black hole's region, but it is impossible for light to exit. It will inevitably hit the singularity instead. This diagram represents the kind of black hole we are used to seeing in the real world. It accounts for its formation at some specific point in time when the star collapsed. But it is only one piece of the full mathematical description of black holes. In other words, it is the lone ice cream cone of black hole diagrams. So what happens if we forget the real world for a moment and imagine an ideal black hole with an infinite past? What is the black hole analog of the full mathematical cone? The math describes not just our universe and the black hole. It also describes something that looks like the inverse of a black hole, a place with a singularity in its past, not its future. And if you draw the motion of light rays, you see that it is straightforward for light to leave this region, but it can never enter it. This type of region is exactly what we would call a white hole, the space-time analog of a traffic cone. But that is not all. If you look beyond the white hole, the math also describes a patch of space-time that is a parallel universe entirely disconnected from our own. The upshot of all this is that the same mathematical equation that describes our universe and the black hole also describes a parallel universe and a white hole. This does not mean that every black hole comes attached to a white hole. Just like with cones, the real universe can contain chopped up pieces of the full mathematical solution. But it does mean that even if white holes are less common, or even if there are none connected to our universe at all, it doesn't make them any less scientific. They are equally consistent with the laws of physics. If you imagine that ice cream cones remained extremely popular while traffic cones became difficult to produce and were phased out of existence, that doesn't make the idea of a traffic cone any less real. This is more or less the status of white holes today. The notion makes perfect sense. But it is possible that any white holes that existed in the past were unstable and were similarly phased out of existence. The dream of the universe holds many silent shapes. And if you are wondering whether there could be some more stable white holes that have just escaped our sight, you are not the only one. But before we drift into that thought, we must remember the three simple properties of a black hole: its mass, its charge, and its spin. The quiet diagrams we have imagined so far only described the simplest kind: a black hole that was electrically neutral and completely still. The diagrams for charged or spinning black holes are much more intricate and much more exciting because they completely alter our understanding of that final crushing point, and they give rise to new and fascinating regions of space-time. Let us have a look at the Penrose diagram for a spinning black hole as an example. Instead of 4 distinct regions, there are now many more repeating themselves in an infinite pattern of universes. A reflection in 1,000 mirrors. The regular universe. The black hole, the white hole, and the parallel universe are still there. But now that the black hole is spinning, its geometry no longer has an unavoidable singularity in its future. And the white hole similarly loses the singularity that existed in its past. So what actually happens after you cross the event horizon of a spinning black hole? At first, you will be drawn towards the center just as you would expect. A slow, inevitable fall. But eventually, you will cross a second threshold, a place known as the inner horizon. Beyond this second inner shore, the geometry of space-time unwraps and lets you stop yourself from falling even deeper. In these innermost regions, you can float freely towards or away from the center. You could even touch the singularity if you wanted to, though it would not be a point anymore. Here in the heart of a spinning black hole, the singularity takes the shape of a ring, a circle of infinite density. Here in this quiet innermost region of a curved, rotating space-time, you are officially in a wormhole, a tunnel between worlds. And at this point, you are faced with a bit of a fork in the road. Two quiet paths leading away from this still center. One option is to keep moving inward and go around the ring singularity. This path would take you to a new region in the diagram. But it is quite possible that the existence of this path is a flaw in our understanding rather than a true description of reality. Because going in even a single loop around the singularity can lead to strange paradoxes where you might visit your own past, a dream that perhaps should not be followed. A safer bet would be to turn around and move outwards, crossing back through the inner horizon that you just came out of. This would take you into a white hole, and it would then carry you like a leaf on a gentle current, all the way out to a brand new universe. A universe similar in structure to the one you started out in, but sadly, without your friends or family waiting for you. In fact, by the time you get here, your old universe will have already experienced an infinite amount of time. You would be living in a whole new definition of the future. The journey continues into a time beyond our own. And so let us gently step back from this dream of a journey. As beautiful as it is to imagine, it is a path that in practice you probably could not survive. The very tunnel itself is a delicate thing, a breath held in the equations of space-time, and the slightest disturbance, the presence of a single traveler, might be enough for that breath to be released and for the path to close forever. So how much of this beautiful mathematical structure can we expect to see in the real world? Spinning black holes with their silent event horizons appear to be everywhere in the universe. But what goes on inside of them is still largely unknown. The clean, perfect lines of the diagrams, they imagine a black hole that has existed forever, a perfect, eternal shape. But the black holes in our universe are born from chaos, from the turbulent, fiery collapse of a dying star. And so, the assumptions that went into making these perfect maps are violated. The universe around a real black hole is not perfectly symmetric. It does not exist in a perfect vacuum. And the laws themselves, the beautiful equations that draw these maps for us, may only be an approximation. They may grow quiet and fade as they approach the immense pressure of the singularity. where the curvature of space becomes extreme. So there is a good chance that some of the predictions of the diagram, especially the most problematic ones, the ones that involve paradoxes and journeys into the past, are not real features of our highly curved space-time. They may be ghosts in the mathematics, echoes of a possibility rather than a destination. But while the path through the center may dissolve, the existence of white holes is more of an open possibility, leaving plenty of room for gentle speculation. A question that still hangs softly in the quiet of the cosmos. One hypothesis that has recently gained some traction is that a white hole is born whenever a black hole dies. And no, this is not some magical story of reincarnation. It is a genuine attempt to understand the full life cycle of these strange objects. You see, even an isolated black hole in an otherwise empty space will continuously emit that faint warmth, that Hawking radiation, causing it to gradually shrink and lose its mass over an immense stretch of time. But once the black hole shrinks to a super tiny size, about the weight of a grain of salt, we have no way of predicting what future awaits it. At least, not without a full theory that can unite the immense scale of gravity with the tiny world of quantum mechanics. This is where a theory called loop quantum gravity comes in. It is a proposed link between these two worlds, in which space itself is made of discrete, tiny loops. And in short, the equations of this theory predict that instead of continuing to shrink even smaller, such a tiny black hole is instead more likely to quantum tunnel, to pass through a barrier of reality and become a white hole. It would then spew its contents back out into the universe over an extended period of time. A slow, patient return. And incredibly, even though this white hole will be similarly small and light, it can contain an enormous amount of information because its interior geometry will have been stretched into a thin, deep space with an extremely large volume. This quiet store of memory could potentially open a pathway for any information that falls into a black hole to be recovered in the distant future. It is a possible solution to a decades-long problem in physics known as the information paradox. And as the white hole releases this information, it begins to slowly fade out of existence. The space-time around it loses its curvature and its life cycle comes to a quiet, peaceful close. But before this thought comes to a close, let me leave you with one last gentle image. In the theory of general relativity, our whole universe is predicted to have had a singularity in its past, 14 billion years ago at the moment of the Big Bang. In this way, our universe is like a vast, uncharged stationary white hole. But if a white hole can be born when a black hole collapses, could the same be true about the creation of our universe? Could it be that our expanding universe was born from the ashes of an older contracting space-time. The thought widens like the universe itself. As strange and as deep as this seems, the quiet language of the universe suggests that it may well be the case. That our beginning was not a sudden violent explosion, but a gentle, silent bounce. A soft transition from a universe that came before. There are so many different ideas for how this quiet passage could have happened. So many different dreams of the universe's own birth, that the story of our beginning may hold more surprises, yet waiting for us in the soft light of the past. Our journey tonight has been a long and quiet one. We have drifted from the heart of a dying star through the silent spinning whirlpool of space-time to the very edge of what we know. We have watched shadows form and fade and listened for the faint, warm whisper of light returning from the darkness. And now we return, back from the far reaches of the cosmos, back to the gentle, quiet rhythm of your own breath. The universe too has its own slow breath, its own cycles of light and shadow, of waking and of rest. The stars continue their silent dance. The galaxies spin in their slow cosmic tide. And the deep, quiet space between them holds the promise of dreams yet to come. Thank you for drifting with us here at Sleepy Facts. May your own rest be as deep and as peaceful as the silent, starlit dark. Good night.